In the last video, we began the process of writing our very own homemade vector class. And we got as far as being able to write the square bracket operator, .at, push back, and pop back, as well as being able to retrieve the size, and to construct a fixed size underlying storage array. And we use a C-style array for that, because what alternative do we have? How else do we store a sequence of elements? I mean, we could use the vector from the standard library, but that seems sort of like circular logic. And hopefully by the end of this, we're sort of extra thankful that the vector class and our own homemade vector class cover up the need to use C-style arrays. Before we talk, though, about allowing the vector to resize itself dynamically, we've got one other errand to run, which is I have rewritten this print vector function to accept its argument by constant reference. In the last video, it just accepted a plain reference. But we know that we like passing vectors around the program by constant reference, and it's good practice to pass something by constant reference if you know it doesn't need to be modified. But if I do this, if I accept the argument by constant reference, the compiler gets some heartburn. So the compiler has a problem with this that we now have to remedy. Now we should already understand, going back to week 6, that there is something we pretty much have to do here. So there is one path we need to be taking, which is we have to add the const keyword in various places. I just want to show off how we do that in the vector type, and also show off a rather odd feature that you will notice in a lot of collection types, including maybe the ones you write for assignments, where we end up with what appear to be two identical versions of a function, because we have to have one that works for the constant case and one that works for the non-constant case. I want to show that off. I want to show off how we have to make an arbitrary, complicated object like a vector constant safe. So what I need to do is make it so that if I pass the vector in a context where it becomes constant, we can still use those functions that make sense. Obviously, there are some functions on a vector that I shouldn't ever be using with a constant vector. So it would make no sense to call push back on a vector that is constant, because that modifies the vector. On the other hand, asking the vector for its size is pretty harmless if the vector is constant. The vector doesn't change just because I asked that question. And .at is basically harmless in the right context. So there are some ways that I could use .at that don't make sense on a constant vector. This, for example, on line 96, wouldn't make sense for a constant vector. I should never be allowed to modify an element of a constant vector. But if I use .at simply to read an element, that should be okay. So I want to make my functions constant. I want to allow certain functions to be used on constant vectors. And the first one, the obvious one, is the size function. So I just add the const keyword to this. On the other hand, what do I do with square brackets and .at? So it doesn't make sense to write this, because I know that I am breaking the contract if I do this. Notice how if I return a reference, an unconstrained reference to an element of my array, somebody who receives the reference could modify it. Even if the compiler tolerates this, and this is actually an example of a case where the compiler doesn't quite know what I'm doing and will likely let me compile this. It will likely say, okay, fair enough, I'll take your word for it, that's constant. I should know this is not obeying the spirit of the law. So if I return a non-constant reference to an element of my array, somebody could modify the array. That means this is not truly a constant function. So I'm in trouble if I do this. So what is my alternative? I want some people to be able to modify elements with square brackets, those people that have a non-constant vector. But those people that have a constant vector shouldn't be allowed to modify elements. So let's try a couple variations of this. So the first one is, okay, I'll make the function constant, and I'll say it returns a constant reference to an element. That way, yes, you get back a reference to an element, but you can't modify it. So I can be assured, I can sleep well knowing that this square bracket operator on a constant vector will never be used to modify elements. I can do something similar for the .at function. So it returns now a constant reference, not a reference. That means that although you do get a reference to an element, you could never modify the element using this. And we'll just skim over the errors before I compile again. So here's an error involving .size. So it says, sorry, you can't pass a constant vector as the this argument. So it's here, this is its cryptic way of pointing out that inside the function, this pointer would be constant, and you can't modify something that's constant, obviously. And then same thing here, .size doesn't work because .size is not a constant function, but the type of this would be a constant vector, which makes no sense. But then also .at. So on line 72, it's complaining about .at because .at isn't constant. But here, I've marked it as being constant. Let's see what happens if I compile now. Here it has two other errors. Notice how the errors have been transposed down to line 95 and 96. It's no longer complaining about line 72. It doesn't complain about these because the size function is now constant. On line 72, .at is no longer a problem because I've said, don't worry, the .at function is constant. It is safe to use on a constant vector. The problem is if I go down to line 95 and 96 with square brackets and .at, I'm trying to assign to the result of the square bracket operator or the result of the .at function. And here the compiler is saying, I'm sorry, you can't assign to the result of the square brackets because the square brackets returns a constant reference. And you can't assign to the result of .at because that returns a constant reference. So what do? I want to have my cake and eat it too. I want somebody to be able to use .at to modify an element if they don't have a constant vector, and I want somebody to be able to use .at to read an element but not modify it if they do have a constant vector. So here's a solution. I could make two almost identical .at functions. And this is a case where our usual function overloading logic needs a little bit of refinement. It turns out the compiler can tell the difference between these two things. They do have the same name and the same arguments. And when we first introduced function overloading, we didn't know about constant functions. The compiler, if it notices this, will choose whichever function is the least restricted version that I'm allowed to use. So if I have a non-constant vector, the compiler will say, well, this function is valid for a non-constant vector, so we'll use this one. If I have a constant vector, this function, the least restricted function, isn't valid, because you can only call constant functions on a constant vector. So in this case, the compiler would say, if you have a constant vector, you have to use this version. So here I'm allowed to provide two identical functions, or two functions with the same signature that have different properties, where one of them is for a constant object and one of them is for a non-constant one. And I can do that. It seems a bit redundant, and it is. There are a couple of ways around it using some deep magic, but for our purposes, although it's a little bit redundant, they're short functions, this is, I think, a pretty, digestible way of handling it. I can tolerate this. And so we'll try that. And we notice this does allow us to have our cake and eat it too. I've now defined parallel tracks that we can take. One if you have a constant vector, one if you have a non-constant vector. And all the restrictions still apply. So for example, if I try and use .at inside the print vector function where I know the vector is constant, if I try and modify something, the compiler will still catch it. It will still tell me, sorry, you can't modify that. Your vector is constant here. And I can still use .at to read the element because I have a constant version that allows me to read an element. Down in main, I am allowed to still use square brackets and .at to modify things. So although it was a little bit clunky and it did require me to do some duplication, something that should always worry me a bit, this is, I think, a pretty readable solution given that I have short functions. Okay, so in the next video, we're going to talk about how do I make the vector exhibit that classic vector behavior of growing and shrinking as the situation requires. As I add more elements, the vector can keep taking them. As I remove elements, the vector seems to be able to seamlessly adapt to that.